Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The actuary and the biosphere. A peculiar intellectual duality defined the career of Alfred James Lotka. One finds him, day by day, seated at a desk within the Statistical Bureau of the Metropolitan Life Insurance Company in New York, a man immersed in the precise, sober calculus of human mortality. His professional world was one of tables, probabilities, and the predictable rhythm of large numbers applied to life expectancies and premium calculations. This was the meticulous, earthbound work of an actuary. Simultaneously, within the quiet laboratory of his own mind, this same man was constructing a vision of life on a scale of breathtaking grandeur, applying the universal laws of physics to the entire teeming, struggling biosphere. His life's work represents a profound synthesis, wedding the pragmatic mathematics of the insurance office to a cosmic perspective on evolution and ecology. He was a thinker who saw the same fundamental principles governing the lifespan of a single policyholder and the energetic pulse of a whole planetary ecosystem. To appreciate the scale of Lotka's contribution, one must recall the state of the life sciences in the early 20th century. Biology was a discipline of immense descriptive power. Following Darwin, its practitioners were masters of observation, classification, and the grand narrative of natural selection. They could trace the intricate genealogies of species, document the exquisite adaptations of organisms to their environments, and compile vast catalogues of life's diversity. The science, however, operated largely through qualitative reasoning. It possessed a powerful explanatory story, the struggle for existence, yet it lacked a unifying quantitative language. The physicist could describe the universe through the elegant formalisms of thermodynamics and mechanics. The chemist could predict reactions with the precision of stoichiometry. The biologist, by contrast, had few such tools. The central question remained unanswered. Could the complex, seemingly chaotic world of living things be subjected to the same rigorous mathematical analysis as the inanimate world? Was there a physics of life? Lotka's definitive answer to this question arrived in 1925 with the publication of his masterwork, Elements of Physical Biology. The very title was a declaration of intent, a bold fusion of two fields that had long maintained a respectful, if distant, relationship. Within its pages, Lotka laid out a comprehensive theoretical framework for understanding all of biology as a problem in energy transformation. He proposed that the entire biosphere, from the smallest bacterium to the largest whale, from the densest forest to the most barren desert, could be viewed as a single colossal thermodynamic system. He called it the Great World Engine, a machine whose primary function was the capture, degradation, and circulation of solar energy. This perspective was revolutionary. For Lotka, evolution itself was a physical process governed by thermodynamic imperatives. The principle of natural selection, in his formulation, was a special case of a more general physical law. Organisms, and indeed entire ecosystems, compete. The victors in this competition are those configurations of matter that become most effective at capturing available energy and transforming it into biomass and activity, thereby maximizing the total energy flux through the system. In his view, the development of chlorophyll, the evolution of warm-bloodedness, the rise of human civilization, all were episodes in a planetary drama whose central plot was the relentless optimization of energy flow. He saw life as a clever eddy in the universal river of entropy, a system that locally organizes and builds complexity by accelerating the degradation of energy globally. This reframed the struggle for existence from a mere biological contest into a fundamental physical principle. The conceptual tools Lotka deployed were drawn directly from his deep training in physics and chemistry. He recognized that the dynamics of populations bore a striking resemblance to the dynamics of chemical reactions. He began to think of an ecosystem as a vast reaction vessel. A species was analogous to a chemical compound, its population size representing its concentration. The interactions between species, predation, competition, symbiosis, were equivalent to chemical reactions, each with its own characteristic rate. A plant converting sunlight, water, and carbon dioxide into organic matter was a photosynthetic reaction. An herbivore consuming a plant was a subsequent reaction, transferring mass and energy up the food chain. To give this vision mathematical substance, Lotka turned to the language of change, the differential equation. This was his instrument of choice, borrowed from the study of chemical kinetics and celestial mechanics. He began to write down systems of equations that described how the concentrations of one species would change over time as a function of the concentrations of others with which it interacted. For instance, the rate of growth of an herbivore population would be proportional to the amount of available plant life, while simultaneously being diminished by the prevalence of its predators. Each term in his equations represented a flow of matter and energy, a link in the intricate web of what he termed the metabolism of the ecosystem. The publication of Elements of Physical Biology was a landmark, though its full impact took decades to materialize. For many biologists of the 1920s, steeped in a tradition of fieldwork and morphology, its abstract, mathematical formalism was alien territory. It was a book that demanded a new kind of thinking, a fluency in both differential calculus and natural history. Yet, for a forward-looking minority, it was a revelation. It provided the first comprehensive blueprint for a truly quantitative, theoretical ecology. It established the conceptual foundations for what would later become the fields of systems ecology, ecological energetics, and biogeochemistry. His work demonstrated that the economy of nature could be audited with the same rigor as the economy of a nation, using the universal currency of energy. This grand, holistic vision of the biosphere as a single, integrated physical system was Lotka's foundational achievement. He provided biology with a new set of first principles, grounding it firmly in the bedrock of thermodynamics. Within this sweeping framework, however, he also developed specific, exquisitely focused models that would come to define the birth of a new discipline. He turned his mathematical lens from the world engine as a whole to the intricate rhythmic dance of its component parts, uncovering the elegant mathematical pulse that governs the relationship between the hunter and the hunted. The rhythmic dance of populations. This grand, holistic vision of the biosphere as a single, integrated physical system was Lotka's foundational achievement. He provided biology with a new set of first principles, grounding it firmly in the bedrock of thermodynamics. Within this sweeping framework, however, he also developed specific, exquisitely focused models that would come to define the birth of a new discipline. He turned his mathematical lens from the world engine as a whole to the intricate rhythmic dance of its component parts, uncovering the elegant mathematical pulse that governs the relationship between the hunter and the hunted. For centuries, naturalists and outdoorsmen had observed a curious and persistent pattern in the wilderness. The populations of certain animal species appeared to wax and wane with a mysterious regularity. The most famous and meticulously documented example came from the fur-trapping records of the Hudson's Bay Company in Canada. Over decades, the data revealed a hauntingly periodic fluctuation in the pelts of the snowshoe hare and its primary predator, the Canadian lynx. As the hare population boomed, the lynx population followed, feasting on the abundance. Then, as the burgeoning lynx population consumed the hare population would crash, and the lynx, deprived of their food source, would soon follow into scarcity. The cycle would then begin anew, an ecological ballet playing out over a roughly 10-year period. This phenomenon was understood through the descriptive lens of Darwinian struggle, a narrative of feast and famine. Yet, a quantitative predictive theory capable of explaining the mechanism behind these persistent oscillations remained elusive. The question lingered: was this rhythm a product of external forces, like climate cycles or disease, or was it something intrinsic to the very relationship between predator and prey? Lotka's great contribution was to provide the definitive answer, and in doing so, to transform ecology from a descriptive science into a mathematical one. He abstracted the raw, chaotic detail of the natural world into its essential dynamic components. His approach centered on the idea that the core of the interaction could be captured by a set of differential equations, mathematical statements that describe how quantities change over time. This intellectual leap was immense. It treated populations as continuous variables and their interactions as rates, allowing the powerful tools of calculus to be brought to bear on a biological problem for the first time with such clarity. In his 1925 masterwork, Elements of Physical Biology, Lotka presented his formulation. It consists of a pair of coupled, non-linear equations, a landmark in the history of theoretical biology. Imagine two populations, one of prey, which we can call X, and one of predators, which we can call Y. Lotka proposed that their interdependence could be described as follows. The first equation governs the prey population. The rate of change of the prey, expressed as dx dt, is determined by two opposing forces. The first term is alpha times x. This represents the prey's own potential for growth. In the absence of predators, the prey population would grow exponentially at a rate alpha. The second term is a negative one, minus beta times x times y. This term represents the loss of prey due to predation. Its logic is beautifully simple. The number of encounters between predators and prey is proportional to the product of their populations, x times y. The constant beta is a coefficient representing the efficiency of the predator or the likelihood that an encounter results in a kill. The complete equation reads: the rate of change of the prey population equals its intrinsic growth rate minus the rate of its consumption by predators. The second equation mirrors this logic for the predator population. The rate of change of the predators, dy dt, also has two components. The first term is delta times x times y. This represents the growth of the predator population. Like the predation term in the first equation, it is proportional to the number of encounters between the species. The constant delta represents the efficiency with which predators convert the prey they consume into new offspring. The second term is again a negative one, minus gamma times y. This describes the natural death rate of the predator population. In the absence of prey, the predators would die out exponentially at a rate gamma. The complete equation for the predators thus captures their growth as a function of the food supply and their decline from natural mortality. The genius of these equations lies in their coupling. The fate of each population is inextricably linked to the size of the other. The prey population's growth is limited by the predators, and the predator population's growth is fueled by the prey. When solved, this system of equations produces a remarkable result. The two populations oscillate through time, one lagging behind the other in a stable, repeating cycle. The lynx and the hare were a mystery of the Canadian wilderness. They were a solution to a system of differential equations. Lotka had demonstrated that the rhythmic dance was an endogenous property of the interaction itself. It required no external pacemaker. The predator and prey generated their own self-sustaining beat. In a striking instance of simultaneous discovery, the Italian mathematician Vito Volterra independently derived a virtually identical set of equations around the same time. Volterra was prompted by a query from his son-in-law, the marine biologist Umberto di Ancona, who had noticed that the proportion of predatory fish caught in the Adriatic Sea had increased during World War I, when overall fishing had been reduced. Volterra's model explained this counterintuitive observation perfectly. Reduced fishing pressure on the prey, fish allowed their populations to grow, which in turn fueled a larger boom in the predator populations. That two brilliant minds working in different countries and motivated by different biological puzzles, one terrestrial, one marine, arrived at the same mathematical structure speaks volumes about the fundamental truth the equations captured. The Lotka-Volterra model, as it is now universally known, is a cornerstone of modern ecology. Of course, it is an idealization. It assumes a perfectly uniform environment, that predators never become satiated, and that the two species interact in a vacuum, isolated from the rest of the ecosystem. Yet its value resides precisely in this elegant simplification. It isolates a fundamental ecological mechanism and reveals its dynamic consequences with pristine clarity. It provided the conceptual blueprint for all subsequent population modeling. Today, more complex and realistic models used in conservation biology, pest management, and epidemiology are direct intellectual descendants of Lotka's original formulation. The famous César models, which describe the spread of infectious diseases by tracking susceptible, infected, and recovered individuals, are built upon the very same logic of coupled differential equations governing interacting populations. By giving ecology its first great law of motion, Lotka did something profound. He showed that the living world, for all its complexity and apparent randomness, was amenable to the same kind of mathematical reasoning that Newton had applied to the planets. He revealed a clockwork precision ticking away beneath the surface of the struggle for existence. This same powerful impulse, the drive to uncover the quantitative laws governing living systems, would soon lead him to apply his analytical gaze to another, uniquely complex population. He turned from the dynamics of hares and lynx to the dynamics of human societies, seeking the mathematical principles that govern our own growth, our age structure, and even the very rate at which we produce new knowledge. The measure of man and mind having established the profound impact of Lotka's ecological models, particularly his pioneering work with the Lotka-Volterra equations, we now shift our focus to another arena where his mathematical prowess left an indelible mark, the quantitative social sciences. Here his contributions to formal demography and the nascent field of bibliometrics reveal a remarkable consistency of approach, a deep-seated commitment to uncovering the underlying mathematical structures governing complex systems, whether biological or social. Actuarial science, at the turn of the 20th century, relied heavily on crude life tables. These provided a snapshot of mortality rates across different age groups, but lacked a robust theoretical framework capable of connecting these rates to a population's overall growth trajectory. Predicting long-term population dynamics remained a significant challenge, hindering efforts in public health planning and resource allocation. Lotka addressed this directly, developing what would become known as stable population theory. This theory elegantly demonstrated that a population subjected to constant age-specific fertility and mortality rates will, over time, converge to a stable age distribution and a characteristic rate of growth. This was far from a trivial observation. It required the development of sophisticated mathematical tools, most notably Lotka's integral equation of population renewal. This equation, a masterpiece of mathematical modeling, provided the analytical machinery to dissect the intricate interplay between age structure, birth rates and death rates, allowing for precise projections of future population sizes and age distributions. The equation itself is a testament to Lotka's mathematical skill, a complex expression that captures the continuous renewal of a population through births and deaths across age cohorts. Its solution reveals the stable age structure and intrinsic growth rate of the population, providing a powerful predictive tool for demographers and planners alike. The impact of Lotka's work on demography is immeasurable. His integral equation and the broader theory of stable populations remain central to the field, providing the underpinnings for modern population projections and analyses. Actuarial science, the field concerned with assessing and managing risk associated with life events, owes a considerable debt to his work. The mathematics that allows insurance companies to predict mortality and manage risk is in large part a direct consequence of the mathematical foundations Lotka laid. His work allows for more accurate assessments of longevity, informing crucial decisions in areas ranging from pension planning to public health resource allocation. Moving beyond the dynamics of human populations, Lotka extended his quantitative approach to a seemingly disparate domain, the world of scientific publications. Prior to his work, an understanding of the distribution of scientific contributions among researchers was largely absent. Was scientific productivity concentrated among a select few highly prolific individuals, or was it more evenly distributed across a broader range of scholars? This was a question of fundamental importance in understanding the dynamics of scientific progress itself. Lotka's innovative approach involved analyzing publication data, specifically the number of papers authored by different scientists. Through meticulous statistical analysis, he discovered a remarkable regularity, a statistical law that now bears his name, Lotka's law. This law, an inverse square law, states that the number of authors making contributions is approximately 1 over n squared of the number of authors making a single contribution. In simpler terms, many scientists publish only a few papers, a smaller number publish a moderate number, and a very few publish a large number. This seemingly simple pattern revealed a fundamental regularity in the distribution of scientific productivity, a quantitative fingerprint of the scientific enterprise itself. Lotka's law was a pioneering achievement in the nascent field of bibliometrics, the quantitative study of scholarly literature. It provided a crucial lens through which to analyze research output, understand the structure of scholarly communication, and gauge the impact of individual scientists and research institutions. Its enduring relevance is evident in the continued use of Lotka's law in scientometrics, the application of quantitative methods to the study of science as a social phenomenon. Researchers today regularly employ this law to analyze citation patterns, assess research productivity, and evaluate the impact of different research areas. The insights gained from this simple yet powerful law continue to shape our understanding of the production and dissemination of scientific knowledge. The remarkable aspect of Lotka's contributions to both demography and bibliometrics is the underlying unity of his approach. In both cases, he sought to identify the fundamental mathematical principles governing the dynamics of complex systems. He demonstrated a remarkable ability to translate seemingly disparate phenomena into precise mathematical models, revealing the hidden order beneath the surface of apparent complexity. This analytical power, this ability to see the mathematical threads connecting seemingly disparate systems, would soon lead him to formulate his most ambitious and far-reaching theoretical contribution, a vision that would unite his diverse works under a single powerful conceptual framework. This overarching framework, a grand synthesis of his life's work, will form the subject of our final exploration. The energetic imperative and a unified vision. Lotka's exploration of population dynamics and scientific productivity yielded profound insights, revealing fundamental mathematical structures governing the growth and distribution of both human populations and scientific knowledge. These insights, however, served as a prelude to his most ambitious intellectual endeavor, the formulation of a universal principle governing the evolution of biological systems. Darwin's theory of evolution by natural selection elegantly explained the mechanism of adaptation, the differential survival and reproduction of organisms based on their traits. Yet, a crucial question remained unanswered. What specific quantity, what physical property, is actually being maximized by this evolutionary process? What, in essence, are successful biological systems selected for? Lotka's response to this challenge was both audacious and profound. He proposed that the driving force behind evolution is the maximization of power, a principle he termed the evolutionary principle of maximum power. This wasn't a mere conjecture. It represented a deep integration of biological principles with the fundamental laws of physics, specifically the second law of thermodynamics. He argued that the struggle for existence, the central theme of Darwinian evolution, could be reframed as a competition for energy flux, for the efficient capture and transformation of available energy into useful work. Organisms, species, and entire ecosystems, in Lotka's vision, are engaged in a relentless pursuit of energy, striving to optimize the flow and utilization of this fundamental resource. This perspective offered a novel framework for understanding evolutionary processes. Instead of viewing natural selection solely through the lens of reproductive success, Lotka's principle emphasized the underlying physical constraints and energetic imperatives that shape the trajectory of life. He saw evolution as a process of increasingly efficient energy capture and utilization, a drive toward greater power in the thermodynamic sense. His approach wasn't simply a reinterpretation of existing evolutionary theory, it was a radical attempt to ground the very foundations of biological evolution in the fundamental laws of physics. The mathematical formulation of this principle, while complex, reflects Lotka's deep understanding of both biology and mathematics. He employed sophisticated mathematical tools to model the energy flow within and between biological systems, seeking to identify the conditions under which maximum power is achieved. This involved the development of intricate models incorporating factors such as resource availability, energy conversion efficiency, and the interplay between different species within an ecosystem. The elegance of his approach lay in his ability to bridge the gap between the abstract world of mathematics and the concrete reality of the living world, translating complex biological interactions into precise mathematical equations. Lotka's principle of maximum power, though initially met with some skepticism, has gained increasing recognition in recent decades. It serves as a precursor to Howard T. Odum's maximum power principle, a cornerstone of modern systems ecology. This principle has found applications in diverse fields, including theoretical biology, ecological modeling, and the study of non-equilibrium thermodynamics. The principle's enduring relevance stems from its ability to provide a unifying framework for understanding the dynamics of complex systems, whether biological, ecological, or even social. It emphasizes the fundamental role of energy in shaping the structure and function of these systems, revealing a common thread that connects seemingly disparate phenomena. The enduring legacy of Alfred James Lotka extends far beyond his specific contributions to demography, bibliometrics, or even his principle of maximum power. His true genius, perhaps, lies in his holistic approach to scientific inquiry, his ability to synthesize seemingly disparate fields of knowledge into a unified vision. He possessed a remarkable capacity to see the underlying mathematical principles that govern the dynamics of complex systems, whether those systems are human populations, scientific publications, or entire ecosystems. His work transcends the boundaries of traditional disciplinary divisions, foreshadowing the interdisciplinary approach that characterizes much of modern science. Lotka's work offers a compelling example of the power of systems thinking, the ability to recognize the interconnectedness of seemingly disparate phenomena. He was a pioneer in the development of mathematical models for complex systems, decades ahead of the formal emergence of complexity science. His insights into the dynamics of population growth, scientific progress, and the evolution of life itself, though expressed in the language of mathematics and physics, resonate deeply with the modern understanding of complex systems, their emergent properties, and their inherent unpredictability. In essence, Lotka's contribution was not merely a series of specific mathematical models or theoretical principles. It was a profound shift in perspective, a recognition of the underlying unity of seemingly disparate phenomena. He demonstrated the power of mathematical modeling to reveal the hidden order within complex systems, providing a blueprint for the interdisciplinary science of complexity that would flourish in the decades following his death. He was a visionary, a pioneer, a quintessential systems thinker, whose work continues to inspire and challenge us today. His legacy is not confined to any single equation or theory. It is the enduring power of his unified vision, his profound insight into the fundamental principles governing the dynamics of complex systems, and his unwavering belief in the power of mathematics to illuminate the workings of the natural world. He stands as a testament to the enduring influence of a truly original and insightful mind.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.